Welcome to the Explainer Focused Learners. Today we are tearing down something absolutely fascinating, the Aviator AI platform. If you've ever wondered how artificial intelligence is moving beyond just chatting with us and actually stepping into the realm of real-time, high-speed, autonomous decision-making in super volatile environments, well, you are in for a treat. We are going to deconstruct exactly what this system is, look closely at its architecture, figure out how it learns, and highlight its biggest advantages.
Here is our roadmap for the teardown. We'll start with 1. Meet the Aviator AI. Then 2. Decoupled microservice architecture. Next up is 3. How the AI learns, followed by 4. Guardrails and risk management. And we'll wrap up with 5. The system's key advantages. Let's get right into it.
Section 1. Meet the Aviator AI, deconstructing the platform.
So here is the million-dollar question. How do you train an AI to make profitable decisions in an environment that is mathematically built to be completely unpredictable? I mean, think about it. We are talking about a crash game where a multiplier climbs and climbs, and then boom, drops to 0 at any random millisecond. The game is literally engineered with a house edge, meaning the mathematical expectation is that you will lose money over time. So how on earth do you build an autonomous system to survive, let alone thrive, in that kind of hostile digital environment?
Well, the answer is the Aviator AI Autonomous Reinforcement Learning Platform. Basically, this is an end-to-end, real-time autonomous ecosystem. It's specifically engineered for 3 main things: live telemetry extraction, which just means pulling data from the game as it happens, dynamic risk evaluation on the fly, and actual decision execution. So it's not just some simple script, right? It's a full-blown ecosystem working together seamlessly. This definition is going to be our foundation for the rest of the explainer.
All right, moving on to Section 2, Decoupled Microservice Architecture, the blueprint of the machine. To really wrap our heads around this architecture, I like to use a biological analogy. The system is split into 4 main decoupled components. First up, the Chrome scraper. These are the eyes of the operation. It uses a mutation observer to actively grab live game results straight from the browser's DOM without any lag. Next, we have the WebSocket bridge, or the nervous system. Built on Node.js and TypeScript, this routes all those events asynchronously in real time. Third is the PyTorch RL engine. This is the brain that evaluates the state of the game and actually makes the call. And finally, observability tools like FastMCP, Prometheus, and Grafana. Think of this as the dashboard where human operators can actually monitor the AI's vitals, stuff like win rates and model confidence, live as it runs.
Now you might be wondering, why separate the brain from the nervous system in the first place? Well, if you cram this all into one giant monolithic system, you'd be dealing with major latency. Every time the AI paused to update its neural network, it would literally miss a game round. But by using a decoupled, asynchronous design, the platform achieves sub-millisecond inference speeds. The brain can train quietly in an independent background queue without bottlenecking the nervous system. It even allows for 0 downtime hot reloads. Seriously, you can update the AI's neural weights on the fly without ever turning the machine off.
Section 3. How the AI learns inside the PyTorch engine.
Before we get into the learning model itself, we really have to respect the underlying math of this environment. In provably fair crash games, every single round is statistically independent. Because of that built-in house edge, the expected payout is always mathematically negative. Past outcomes, they carry absolutely 0 predictive weight on the exact next multiplier. So an AI just trying to guess the next number is going to fail. Raw prediction is impossible here. The AI actually has to learn high-level strategies, recognize complex patterns, and crucially, know exactly when to stay completely out of the market.
To pull this off, the AI evaluates a complex 11-dimensional state vector. It doesn't just look at the last multiplier. No way! It's digesting exponentially weighted moving averages over the last 5, 20, and 50 rounds. It tracks crash densities, meaning how often is the game crashing instantly right now. It even measures Shannon entropy, which basically acts as a mathematical gauge for the game's current level of chaos and volatility. So it's processing these 11 complex data points in a fraction of a second to deeply understand its environment.
Armed with those 11 dimensions, the AI jumps into a continuous reinforcement learning loop. Step 1. Observe the state by ingesting that 11-dimensional vector. Step 2. Select an action. It can completely skip the round or decide to cash out at 1.5x, 2.0, or 3.0. Step 3. Compute the reward. It gets a positive bump for profit, a negative hit for losing a stake, and a massive penalty if it ignores any safety rules. Finally, Step 4. Replay and update. It uses prioritized experience replay to update its PyTorch model weights. This means it specifically hunts down its biggest mistakes to learn from them faster, and then it just repeats this loop relentlessly. The secret sauce making those decisions possible is a very specific neural network architecture called a dueling DQN, or Deep Q network. You see, in an environment where rewards are sparse, a standard neural network really struggles. A dueling DQN is brilliant because it splits the processing into two streams. One stream just looks at how good it is to be in the current state of the game, while the other calculates the advantage of taking a specific action over the alternatives. Oh, and to make it even more cutting edge, they swapped out standard random guessing for something called noisy layers. This injects learnable noise right into the network, letting the AI automatically and efficiently explore new strategies without fumbling around with clumsy randomized guessing.
Section 4. Guardrails and Risk Management, the Protective Shield.
Now, an AI that acts this fast can also lose capital incredibly fast if it makes a mistake. That's exactly where the protective shield comes in. The first line of defense is how the AI sizes its bets, using the fractional Kelly criterion. Instead of betting the same flat amount every time, this is a dynamic formula. It calculates the mathematically optimal position size based on the model's confidence combined with the payout odds. But to minimize variance and prevent the account from completely blowing up, it's forced to use just a fraction of that Kelly suggestion, strictly capping the maximum bet at 5% of the total bankroll. It mathematically protects the capital.
And that feeds right into an even tougher layer of security, the stop-loss circuit breaker. If the session drawdown is under 7.5%, we're in normal operation. The AI calls the shots. Between 7.5% and 14.9%, it drops into a caution state. But look closely at that bottom row. If the drawdown hits 15%, boom, the circuit breaker trips. The risk manager completely cuts off the AI's ability to risk any capital, forcing a skip action on every single round. It absolutely will not allow the AI to bet again until the system's rolling volatility naturally cools off and recovers back below 7.5%. It is basically an unyielding mathematical safety net.
Which brings us to Section 5, the system's key advantages, the competitive edge.
We've looked at the architecture, the brain, and the shield. When we pull all these technical pieces together, here are the core advantages you really need to take away from this explainer. First, that decoupled microservice execution minimizes latency, giving it the sub-millisecond reaction speeds you absolutely need for real-time environments. Second, thanks to prioritized experience replay, the AI doesn't just learn evenly. It's mathematically forced to learn from its most critical, high-impact mistakes faster. Third, the hard mathematical boundaries of the fractional Kelly formula and those circuit breakers physically prevent catastrophic ruin. And finally, its flexible dual load means developers can safely train it offline on millions of simulated rounds before unleashing it into a strict, live production environment.
The Aviator AI platform is really a masterclass in combining high-speed data extraction, advanced PyTorch neural networks, and uncompromising mathematical risk management. It goes to show that AI isn't just about chatting or generating images anymore. As AI transitions from static analysis to real-time, autonomous action, making high-stakes decisions in fractions of a second, it leaves us with one massive, thought-provoking question. What incredibly complex, unpredictable environment will reinforcement learning conquer next? Thank you so much for joining me for this explainer, Focus Learners. Keep exploring, and I'll catch you on the next one.